In Chapter 1, we learned that quantitative data can be discrete or continuous. The number of cans of Coca-Cola sold by the gas station near your house today is an example of a discrete variable. The volume of gasoline sold by the same gas station is an example of a continuous variable. Because quantitative data is always numeric, arithmetic operations are meaningful. In this chapter, we will compute the sample statistics such as the mean, standard deviation, skew, and correlation. The sample mean, or average, provides an estimate of the center of the data. The mean tells you how good you are. Do you have a high or low free throw shooting average? If your average is high, you're considered a good free throw shooter. Other measures of location include the median, mode, quartiles, and percentiles. The sample standard deviation is a common measure of dispersion. It tells you how consistent something is. If you are consistently hitting around 55% of your free throws from game to game, your standard deviation will be small. Although you are bad at shooting free throws, you are a consistently bad one. Other measures of dispersion include the range, interquartile range, and variance. The sample skew indicates whether the distribution of the data appears to be symmetric, skewed left, or skewed right. The sample correlation indicates the likelihood of two variables being related. Winning percentage of the football team and attendance at home football games are positively related. Hence, the correlation is close to 1. In the first part of Chapter 3, we study several measures of location, which includes the mean, median, mode, percentiles, and quartiles. If these measures are computed using sample data, they are called sample statistics. The daily presidential polls leading up to an election are an example of sample statistics, called the sample proportion. If these measures are computed, measures meaning the mean, the mode, percentiles, and quartiles, if they are computed using data from the population, these measures are called population parameters. The result of the presidential election is an example of a population parameter, known as the population proportion. A sample statistic is referred to as the point estimator of the corresponding population parameter. It's a procedure. When you plug numbers into the procedure, you get a numeric value or point estimate of the population parameter. The population mean of a data set is the average of all data values. For example, if we had the people and money and time to ask everyone that worked in America last year how much money they earned, we'd have to add up roughly 140 million workers' earnings and then divide this by 140 million. We use the Greek letter M, which is pronounced mu, to note the population mean. Mean. Which is convenient because mu and mean both begin with the letter M. The letter X with subscript 1 is divided the variable X for element 1. If the first element in the population is George Wilson, who works full-time at Walmart making $15,456 a year, X1 is equal to $15,456. If the second element in the population is Tom Hanks, the actor who makes, $15 million a year, X2 is equal to $15 million. The three dots that follow X2 represent the concept of yada yada yada, or etc., etc., etc. If we don't yada yada yada, we would have to write out all 140 million workers' income in the numerator of the population mean, which wouldn't fit on this particular slide. If the 140 millionth element of the population is Jill Jorgensen, a nurse at a local hospital making $28,845 a year, then XN is equal to $28,845. We divide this sum of 140 million workers' earnings by big N, which is equal to 140 million. Using big N is convenient because the phrase number of people in the population, begins with the letter N. Another way of writing the population mean, mu, involves writing the numerator as xi to the right of the symbol big sigma. Big sigma is the Greek letter capital S, which is convenient because both sigma and sum start with the letter S. Xi equals the earnings of the ith person in the U.S. labor market. Big sigma next to Xi sums up all of the N observations of the data. Again, N denotes the size of the population. We use N for the population because we use little n for the size of the sample, because the sample is a subset of the population being studied. Again, big sigma written next to xi means we sum up the n observations of variable x. The sample mean of a data set is the average of the data values in a sample drawn from the population being studied. Because it's too costly to ask 140 million workers how much they earned last year, we could ask 60,000 people how much they earned. Our government does this each month when it conducts the current population survey, known as the CPS. We used the bar over the letter x to denote the sample mean of the variable x. In cases of multiple variables, we would use a bar over the letter y to denote the sample mean of variable y. Variable x could be, say, the earnings of American workers, whereas y could denote the years of education those workers have attained. The sample mean is a point estimator of the population mean. If the first element in a CPS is Valerie Cochetta, a bank teller making $19,433 a year, X1 is equal to $19,433 a year. If the second element in a CPS sample is Timmy Johnson, an auto mechanic making $18,498 a year, X2 is equal to $18,498 a year. Yada, yada, yada. If the 60th element in the CPS sample is Bart Cooley, a waiter making $13,845 a year, then Xn is equal to $13,845. After adding these 60,000 numbers up, we divide the sum by 60,000. Using little n is convenient because the phrase number of people in the sample begins with the letter n. And little n is reserved for the sample, which is a subset of the population, which is of size big N. Another way of writing the sample mean, x bar, involves writing numerator as xi to the right of the symbol big sigma. Big sigma is the Greek letter for capital S, which is convenient because both sigma and sum start with the letter S. Hence, big sigma next to xi means we sum up all little n observations of the data. Little n, again, is the size of the sample, which is appropriate because the sample is a subset of the population being studied, which is of size capital N. Big sigma written next to xi again means we sum up all n observations of variable x. The most common numerical descriptive statistic is a sample mean. In our Hudson auto repair example, a sample mean is found by summing up all 50 observations of tune-up parts cost. The sum equals $3,949. Dividing this by the size of the sample, 50, yields a sample mean of $78.98. The sample mean estimates the population, or true mean, which in most cases we won't know. The probability that the sample mean is exactly equal to the population mean is 0 because the population mean is some unknown value The sample mean, on the other hand, could theoretically be one of infinite many values on the number line. The median is another measure of central location. It is equal to the mean when the distribution is symmetric. The value in the middle of a data set is the median. If there is no middle number, which occurs when the data has an even number of observations, it is the average of the two middle numbers. To find the median, you first must order the data from minimum to the maximum. Whenever the data has extreme values or is skewed, the median is the preferred measure of central location because it represents the value that splits the distribution into the upper and lower halves. A few extreme large incomes or property values can inflate the mean. The median is a measure of location most often reported for annual income and property value data. Why? Well, consider the incomes of Bill Gates and LeBron James. They are just as likely to be selected in a survey of 50 Americans as you are, because each of us has a probability of being selected of about 1 in 300 million. If they or others with large incomes aren't in the sample mean is probably pretty close to the sample's median. However, if one of them, by chance, shows up at a sample of 50 Americans, then the sample mean is going to be in the millions, whereas the sample median will not. To compute the median for an odd number of observations, say 7, put the data in ascending order as I'm doing here. Then pick the middle number. In this case, the median is 19. 4 observations, or 57% of the observations, are less than or equal to 19. Similarly, 4 observations, or 57% of the observations, are greater than or equal to 19. For odd sample sizes, these percentages get closer to 50% as a sample size increases. To compute the median for an even number of observations, say 8, again, put the data in ascending order as I'm doing here. Then pick the two middle numbers. Here, the two middle numbers are 19 and 26. The median is the average of the two. When there's an odd number of observations in a variable, the median is a member or is an element of that variable. When there's an even number, the median is not in the actual data. Here the median is 22.5. Now, 50% of the observations are less than 22.5. 50% of the observations are larger than 22.5. When you have an even number of observations, the percentages are always going to be 50%. To compute the median for the Hudson Auto Repair example, first note that the sample size is 50, which is even. The data is also in ascending order. So we split the data in two parts. 25 in the lower half and 25 observations in the upper half. Since there is no middle number, the median is found by averaging the 25th, which is 75, and the 26th, which is 76, data values. The median is the average of these two numbers, which is equal to 75.50. In this example, the median is below the mean, which was $78.98. This is typical for distributions that are skewed right, which is the case here. We saw this in Chapter 1, and we will revisit it later in this chapter. The mode is the data value with the highest frequency. Notice that the data from our Hudson Auto Repair example is sorted. Sorting the data makes finding the mode easier. Note, there could be multiple modes, which are going to be near the median and the mean, most likely. The frequencies of 52 and 57 are both equal to 1 because there's only one value each in this data set. All numbers between the minimum and the maximum not in the data set, for example, 53, 54, 55, 56, and so on, all have frequencies of 0. The frequency of 62 is 4. The frequencies of 65, 66, and 67 are equal to 1. The frequency of 68 is 3. The frequency of 69 is 3. 70 has a frequency of 0. 71 has a frequency of 2. 72 has a frequency of 2. 73 has a frequency of 1. 74 has a frequency of 2. 75 has a frequency of 3. 76, 77, and 78 all have a frequency of 1. 79's frequency is 3. 80's is 2. 82, 83 have a frequency of 1. 84 has a frequency of 0. 85 has a frequency of 1. 86 and 87 have a frequency of 0. 88, 89 have frequencies of 1. 90's frequency 0. 91's frequency 1. 90's frequency 0. 93's frequency is 1. 97 has a frequency of 3. 98 has a frequency of 1. 99 has a frequency of 1. 100 has a frequency of 0. 101 has a frequency of 1. 102, 103 have frequencies of 0. 104 has a frequency of 1. 105 has a frequency of 2. 105 or 106 to 108 have frequencies of 0, and then 109's frequency is 1. So the mode is 62 because it has the highest frequency. A percentile provides information about how the data are spread over the interval from the minimum value in the data to the maximum value in the data. Admissions test scores for colleges and universities are frequently reported in terms of percentiles. The pth percentile of a data set is a value such that at least p% of these items take on this value or less, and at least 100 minus p% of these items take on this value or more. The median is a special percentile, namely the 50th percentile, because the median is the value such that at least 50% of the items take on this value or less, and at least 100 minus 50 or 50% of the items take on this value or more. To compute percentiles, first put the data in ascending order, just like we did with the median. Do this from the minimum value to the maximum value. Then compute I, which is the index number that identifies the position of the pth percentile. The pth percentile is the ith value of the sorted data. The index number I is equal to p divided by 100 times the sample size. Now, if I is not an integer, you round I up to the nearest integer. The pth percentile is the value in the ith position of the sorted data. However, if I is an integer, the pth percentile is the average of the value in the ith and the I plus 1th positions of the sorted data. This was the case when we found the 50th percentile, also known as the median, in our Hudson Auto Repair example. Recall that we averaged the 25th and 26th values of the data. Hence, I must have been equal to 25 in that case. The 80th percentile in the Hudson Auto Repair example is found after the data is sorted, which it is. The next number is equal to p divided by 100 times the sample size of n. Now the sample size here is 50, and we want the 80th percentile, so p is equal to 80. This is equal to 40, which is an integer. So the 80th percentile is found by averaging the 40th and 41st data values, which are 93 and 97. This is the 40th observation. That is the 41st observation. Hence, the 80th percentile is equal to the average of 93 and 97, which equals 95. Notice that the 80th percentile of $95 is not in the data set. According to the first part of the percentile definition, at least 80% of the items take on the value of 95 or less. There are 40 values in the red box, all of which are less than 95. 40 divided by 50 is equal to 0.8 or 80%. According to the second part of the percentile definition, at least 100 minus 80, or 20%, of the items take on a value of 95 or more. There are 10 values in the red box, all of which are greater than 95. 10 divided by 50 is equal to 0.2 or 20%. Like the median, which is the 50th percentile, the quartiles of a data set are special percentiles. The first quartile is the 25th percentile, or the median of the lower half of the data. The second quartile is the 50th percentile, or the median of the data. The third quartile is the 75th percentile, or the median of the upper half of the data. The three quartiles split the data into 4 quarters. The first quartile is the 25th percentile. Using the sorted data of our Hudson Auto Repair example, the first quartile is computed by computing its location, which is denoted I. The index number I is equal to P divided by 100 times the sample size. The sample size is 50, and we're looking for the 25th percentile, which is the same thing as the first quartile. Here, I, the index number, is equal to 12.5, which is not an integer. So we round this up to 13. The 25th percentile is the 13th value, which is 69. The third quartile is the 75th percentile. Using the sorted data again, the third quartile is found by computing its location, which is denoted I. With P equals 75, 75th percentile, and N equal to 50, I is equal to 37.5, which is not an integer, so we round that up to 38. The 75th percentile is the 38th value in the sorted data, which is equal to 89. Measures of variability tell you the dispersion of the data. A variable with little dispersion, or variation, is consistent. What do I mean by consistent? Consider 2 bad free throw shooters who average 55% from the free throw line. The first one is named Shaq, and the other is me. We're both bad free throw shooters because good free throw shooters shoot in the mid-90s from the free throw line. Suppose Shaq shoots mostly around 55%, 56%, to 54% from the free throw line every game. Suppose one game I shoot 95%, then I shoot 5%, then I shoot 25%, then I shoot 75%, then I shoot 65%, and then 35%. And I'm all over the place. One could say Shaq may be a bad free throw shooter, but at least he is consistent. He's consistently bad, because the variation in his free throw shooting is very small. I, on the other hand, am not only bad, but I'm also very inconsistent. The coach has no idea what he's going to get from me in a given game. The variation of my shooting is large. Measures of variation or dispersion in data include the range, interquartile range, variance, and standard deviation. All these measures are in the same units as the mean, except for the variance. If the variable is in dollars, the range, interquartile range, and standard deviation are all in dollars, while the variance is in dollars squared. If these measures are computed from sample data, they are called sample statistics. If these measures are computed using data from the population, they are called population parameters. The procedure used to compute a sample statistic is referred to as the point estimator of the corresponding population parameter. Inputting numbers into the formula of a sample statistic, such as a sample variance, provides a point estimate, a number that estimates the population variance. The range of the data is simply the difference in the extreme values of the data set, which are the maximum and minimum values of the data set. For our Hudson Auto Repair example, the range is the difference between the maximum value, which is 109, and the minimum value, which is 52. So the range is $57. 100% of the observations are in the range. The interquartile range gives a measure of variation using quartiles. Instead of taking the difference of the minimum and maximum values of the data, the interquartile range is the difference of the first and third quartiles. The range contains 100% of the data, whereas the interquartile range contains the middle 50% of the data. Unlike the range, the interquartile range is not affected by extreme values. To find the interquartile range, one must find the first and third quartiles of the sorted data. For our Hudson Auto Repair example, recall that the third quartile was $89, and the first quartile was $69. So the interquartile range is their difference, 89 and 69. The difference is 20. And the interquartile range contains 50% of the data. So from 69 to 89, 50% of the observations, at least 50% of the observations are between these two numbers. Population standard deviation, sigma, is the most common measure of variation of a variable computed from data from the entire population. Using small sigma to denote the population standard deviation is convenient because both sigma and standard deviation start with the letter S. Note, population parameters denoted by Greek symbols like sigma and mu. Population standard deviation sigma, unlike the population variance, is in the same units as the population mean, mu. If the population mean is in units of dollars, for example, the population standard deviation is in dollars, but the population variance is in dollars squared. To compute the population standard deviation, sigma must first compute the population variance, because the population standard deviation, sigma, is the square root of the population variance. For this reason, the population variance does not get its own Greek symbol. Instead, we use sigma squared to denote the population variance, which is, or can be thought of as, the average variation. The capital sigma in the numerator of this equation means sum up the stuff to its right. The population mean is denoted mu. The stuff inside the parentheses, the difference between the ith observation of x and mu, is called the ith deviation from the population mean. The stuff to the right of capital sigma is called the ith square deviation from the population mean. The numerator is called the sum of square deviations from the population mean. Notice that I used deviations here instead of deviation. The plural version is used because you are summing up n squared deviations from the population mean, because there are n observations of the variable x in the population. The numerator can be thought of as total variation of x. Capital N in the denominator represents the size of the population. Since we summed up n squared deviations from the population mean, we divide by n to get the average variation, which is also known as the population variance. If the population mean is known, but the population variance is not, the following is a valid measure of the sample variance using data from a sample of size little n. Notice how similar this equation is to the population variance. The only difference is the use of sample size instead of population size, big N. We use little n instead because there are only little n items in the sample, which means we are summing up little n squared deviations instead of summing up big N squared deviations. Since the population mean is unknown in most cases, we use the sample mean instead to compute the sample variance. The above equation is biased. To remove the bias, all one has to do is multiply the right-hand side by n over n minus 1 to eliminate the bias. The n's cancel, and we're left with the textbook equation for the sample variance. Why that equation is biased is beyond the scope of the course, but it has to do with the fact that we're using the sample mean to estimate the population mean, which is why we're subtracting off 1 in the denominator. This is an unbiased estimator of the population variance. The denominator, n minus 1, is called the degrees of freedom. This is a very important concept that we'll get to in chapter 7 and 8. As I mentioned earlier, variance is equal to the standard deviation squared. Hence, the standard deviation is the positive square root of the variance. The standard deviation has the same units as the values in the data set and the mean of the data. If the values in the variable are in dollars, the mean and standard deviation are in dollars too, but the variance is in dollars squared. We understand dollars. What the heck is a dollar squared? For a sample, the sample standard deviation S is the positive square root of the sample variance S squared. If the sample variance is, say, equal to 16, the sample standard deviation is equal to 4. If the sample standard deviation is equal to 3, the sample variance is equal to 9. For a population, the standard deviation, sigma, is the positive square root of the population variance, sigma squared. If the population variance is, say, equal to 25, the population standard deviation is equal to 5. If the population standard deviation is equal to 2, the population variance is equal to 4. The coefficient of variation indicates how large the standard deviation is in relation to the mean. The coefficient of variation for the sample is computed by dividing the sample standard deviation, S, by the sample mean, x bar, multiplied by 100. For a population, the coefficient of variation is computed by dividing the population standard deviation, sigma, by the population mean, mu, multiplied by 100. Now, in either case, because the sample or the population standard deviation and mean all have the same units, the coefficient of variation is unitless. In most cases, a small coefficient of variation means you are good at something and also very consistent at it. If you're a good free throw shooter, you have a high average. The higher the average, the lower the coefficient of variation because the mean is in the denominator of the fraction. If you're also very consistent free throw shooter, i.e., you're one game you hit 9 of 10, the next game you hit 10 of 10, the next game you hit 8 of 8, the next game you hit 10 of 11, you're very consistent. The more consistent you are, the lower the variance is. So a high average and very consistent or low variance means a low coefficient of variation. The sample variance, standard deviation, and coefficient of variation cannot be computed until the mean is computed. In our Hudson Auto Repair example, sample mean was $78.98, the red value. This was computed by dividing the sum of observations, 1 through 50. The first observation, lowest observation was 52, the highest observation was 109, and there are 50 values in this column. That sum is $3,949. You divide that by 50 and you get $78.98. The first deviation from the sample mean is computed by subtracting the sample mean, 7898, from the first observation of x, $52. The first deviation from the mean is equal to negative $26.98. This means that the cost of the tune-up parts on the first invoice is $26.98 below average. We square this value to get rid of the negative sign, which results in a first squared deviation from the sample mean of $727.92 squared. The second deviation from the sample mean is computed by subtracting the sample mean, $78.98, from the second observation of x, $57. The second deviation from the mean is equal to negative $21.98. This means that the cost of the tune-up parts on the second invoice is $21.98 below average. We square this value to get rid of the negative sign, which results in a second squared deviation from the sample mean equal to $483.12 squared. The third, fourth, fifth, and sixth deviations from the sample mean are computed by subtracting the sample mean, $78.98, from the third, fourth, fifth, and sixth observations, all of which are equal to $62. These deviations from the mean are equal to a negative $16.98. This means the cost of the tune-up parts on the third, fourth, fifth, and sixth invoices are $16.98 below average. We square these values to get rid of the negative signs, which results in a third, fourth, fifth, sixth squared deviations from the sample mean equal to $288.32 squared. Repeat this process for the remaining observations, but I'm only showing you the ones for the 7th, 49th, and 50th observations. Hence, the 7th, 49th, 50th squared deviations from the sample mean are equal to 195.44, 677.04, and 901.20 squared dollars. The sum of the 50 square deviations from the sample mean equals 9,592.98 squared dollars. The sample variance S squared is found by dividing the sum from the spreadsheet on the previous slide by n minus 1. The sum of the 50 squared deviations from the sample mean is 9,592.98 squared dollars. We divide this by 49 and we get 195.78 squared dollars. Taking the square root yields the sample standard deviation, which is $13.99. The coefficient of variation is computed by dividing this value by the sample mean, 78.98. Since both are in units of dollars, the dollars cancel. The ratio of these two numbers is 0.1772 or 17.72%. This means the standard deviation is 17.92% of the sample mean. Z-scores are used to determine if observations are outliers and used to compute the skew, which is a measure that indicates whether the distribution of the data is skewed or symmetric. The Z-scores can be used to compute frequencies, which can then be compared to Chebyshev's theorem and the empirical rule. The Z-score is often called the standardized value. I consider it to be the single most important concept in this course. The ith Z-score denotes the number of standard deviations the ith observation of variable x is above or below its mean. It is computed by dividing the ith deviation from the mean by the standard deviation. So it has no units. If variable x's units are dollars, the z-score tells us how many standard deviations the ith observation is above or below average. Whereas its numerator tells us how many dollars the ith observation is above or below the average. The numerator demeans the variable x, shifting the distribution's center from x bar to 0. Dividing by the standard deviation changes the standard deviation from some generic value s to equal 1. An observation z-score is a measure of the relative location of the observation in the data set. If you're looking at two variables, say personal income and age, the deviations from the mean cannot be compared because they are in units of dollars and years, respectively. Suppose your annual personal income and age are $8,455 in 19 years. If the sample means are $8,955 in 20 years, your deviations from the mean would be minus $500 and minus 1 year. Both indicate your income and age are below average. Which one is more extreme? The deviations from the mean cannot tell you this. In order to figure out whether your income is more extreme than your age, you need to divide the deviations from the mean by the corresponding standard deviations. Suppose the standard deviations are $1,000 and 0.5 years. Your income z-score is minus $500 divided by 1,000, which equals negative 0.5 standard deviations. Whereas your age z-score is minus 1 year divided by 0.5 years, which equals minus 2. Your age is 2 standard deviations below its mean, while your income is 1/2 of the standard deviation below the mean. Hence, your age is more extreme relative to your income. Using the sorted Hudson auto repair example, the z-score of the smallest value is equal to the deviation from the mean corresponding to the smallest value in the data set divided by the standard deviation. The smallest value in the data set is $52. The sample mean is 78.98, and the standard deviation is 13.99. The resulting z-score is negative 1.93. This value means observation $52, which is $26.98 below average, is 1.93 standard deviations below average. So 52 is not within 1 standard deviation from its mean, but it is within 2 standard deviations from its mean. Notice that we carried the first deviation from the mean and the first z-score from the previous slide into this table. The second deviation from the sample mean is computed by subtracting the sample mean of 78.98 from the second observation of x, $57. The second deviation from the mean is equal to negative 21.98. This means the cost of the tune-up parts on the second invoice is $21.98 below average. Dividing the second deviation from the mean by the standard deviation, 13.992, yields a z-score equal to negative 1.57. Hence, $57 is 1.57 standard deviations below the mean. The third, fourth, fifth, and sixth deviations from the sample mean are computed by subtracting the sample mean 78.98 from the third, fourth, fifth, and sixth observations of x, all of which are equal to $62. These deviations from the mean are equal to negative 16.98. This means the cost of tune-up parts on the third, fourth, fifth, and sixth invoices are $16.98 below average. Dividing these values by the standard deviation results in third, fourth, fifth, and sixth z-scores, all of which are equal to negative 1.21. Hence, $62 is 1.21 standard deviations below the mean. Repeat this process for the remaining observations, but we only show the ones for the 7th, 49th, and 50th observations. The 7th, 49th, and 50th deviation of the mean are negative $13.98, positive $26.02, and positive $30.02. The corresponding z-values are negative 1, 1.86, and 2.15. Now, the sum of the deviation of the mean is equal to 0. The sum of the z-scores is equal to 0 too. This is because when we're calculating a z-score, the numerator d-means the variable. If we divide the sum by the sample of 50, the result is 0 as well. This means that the mean of any set of z-scores is equal to 0. In addition, since each z-score was computed by dividing by the sample standard deviation s, the sample standard deviation of any set of z-scores is equal to 1. This is why the z-score is called the standardized value. A data value that is below average will have a negative z-score. If you are a below average free throw shooter, your z-score is negative. A data value that is above average will have a positive z-score. If you're an above average free throw shooter, you will have a z-score that is positive. A data value that is average will have a z-score equal to 0. If you are an average free throw shooter, your z-score is equal to 0. As I said earlier, I believe the z-score is the single most important concept taught in elementary statistics. It can be used to help determine the shape of the distribution. A symmetric distribution will have a skew equal to 0. Left skewed distributions will have a negative skew, while right skewed distributions will have a positive skew. The formula for computing skewness for data is somewhat complex. Skewness is easily computed using statistical software. However, a skew is just the average, essentially, of z-scores if the sample size is large. Okay. So if the sample size is large, say the sample size is 1,000. This value here is 1,000. This value here is 999. This value here is 998. 1,000 is approximately equal to 999. So these two numbers here approximately equal 1. And 1 divided by 1,000 is about the same as 1 divided by 998. So when n is really, really large, the ratio of these two numbers goes to 1, and the value of the skew gets really, really close to this value down here. To compute the skew, we need to first compute the 50 z-scores for a Hudson auto repair example, which we've already done. Remember, they added up to 0, and their standard deviation is 1. The first cube z-score is equal to negative 7.17. Now, notice that we're cubing a value. So we have a negative 1.93 times a negative 1.93, which is positive. We take that positive value and multiply it again by negative 1.93, and we get a negative 7.17. So cubing the z-score preserves the sign, the original sign of the z-score. The second cube z-score is equal to negative 1.57 raised to the third power, which equals negative 3.88. The third, fourth, fifth, and sixth cubed z-scores are equal to negative 1.21 raised to the third power, which equals negative 1.79. The seventh z-score is a negative 1. Negative 1 times negative 1 times negative 1 is a negative 1. Now we repeat this for the next set of observations, all the way down to the 49th. The 49th z-score is 1.86. Cubing 1.86 gives 6.43. The 50th z-score, 2.15, cubed is 9.88. The sum of cubed z-scores is equal to 22.567. Dividing this by the sample size of 50 yields an average cubed z-score equal to 0.451. If we take this 22.567, the sum of the cubed z-scores, multiply it by 50, divide by 48 and 49, we'd get a skew equal to 0.4797. So that means that the sample size doesn't have to be very big, 50, for the average cube z-score to be pretty darn close to the actual value of skew. A histogram is a bar graph, but a bar graph is not necessarily a histogram. The bars of a histogram have no gaps between them, and their widths are equal to the width of the intervals used in the frequency table. In the diagram below, the label on the y-axis says frequency. So we're constructing a frequency histogram. Since the frequency of interval 50 to 59 is 2, the bar corresponding to this interval stops at 2. Since the frequency of interval 60 to 69 is 13, the bar corresponding to this interval stops at 13. The frequency of interval 70 to 79 is 16. The bar corresponding to this interval stops at 16. The frequency of interval 80 to 89 is 7. The bar corresponding to this interval stops at 7. The frequency of interval 90 to 99 is 7. The bar corresponding to this interval stops at 7. The frequency of interval 100 to 109 is 5. The bar corresponding to this interval stops at 5. The total area of the red bars is 50. If this were a percent frequency histogram, the red bars would have an area equal to 100. If this were a relative frequency histogram, the red bars would have an area equal to 1. The histogram estimates the true distribution of tune-up parts cost. In most cases, we won't know the true distribution of this variable. The area under the true distribution is equal to 1 for the same reason that bars of a relative frequency histogram have an area equal to 1. Now the skew is approximately equal to the average cube z-score. If skew is equal to 0, the histogram will look symmetric. If skew is negative, the histogram will have a long left tail. If skew is positive, the histogram will have a long right tail. The sample size is 50, n minus 1 is 49, n minus 2 is 48, and the sum of cube z-scores is 22.567. The skew is equal to 0.497. Now that was really close to the average cube z-score of 0.451. That's because n equal 50 is quote-unquote large. Now larger the sample size, the closer the average gets to the actual skew. Now the mean was $78.98. The median was $75.50. The mode was $62. If the distribution was symmetric or had a skew equal to 0, these measures of central location would be all equal or really close to each other. If the distribution is symmetric, the histogram from a sample drawn from the population is probably symmetric too. The mean and median are equal, and the sample skew is equal to 0 or really close to 0. If the distribution is moderately skewed left, the histogram from a sample drawn from a population will likely be slightly skewed left too. The mean will be less than the median, and the sample skew will be between 0 and minus 1. If the distribution is moderately skewed right, the histogram from a sample drawn from the population will likely be slightly skewed right too. The mean will be more than the median, and the sample skew will be between 0 and 1. If the distribution is heavily skewed right, the histogram from a sample drawn from the population will likely be highly skewed right as well. The mean will be more than the median, and the sample skew will be greater than 1. If the distribution is heavily skewed left, the histogram from a sample drawn from the population will likely be highly skewed left too. The mean will be less than the median, and the sample skew will be less than minus 1. Chebyshev's theorem can tell you what the relative frequencies are for being within z standard deviations from the mean for any z larger than 1, no matter what the distribution of the data is. The value 1 minus the inverse of z squared is the relative frequency associated with the within z standard deviation interval. If z equals 2, z squared is 4. Dividing 1 by 4 yields 0.25. Subtracting this from 1 yields 0.75, which, according to Chebyshev's theorem, means at least 75% of the data values will be within 2 standard deviations of the mean. If z is equal to 3, z squared is 9. Dividing 1 by 9 yields 0.11. Subtracting this from 1 yields 0.89, which according to Chebyshev's theorem means at least 89% of the data values will be within 3 standard deviations of the mean. If z equals 4, z squared is 16, dividing 1 by 16 yields 0.06, subtracting this from 1 yields 0.94, which according to Chebyshev's theorem means at least 94% of the data values will be within 4 standard deviations of the mean. Most manufacturing processes are normal or bell-shaped distributions. For example, the volume that is in each 12-ounce bottle of Coca-Cola is normally distributed. Most of the time, the volume in the bottle will be slightly above or slightly below 20 ounces. Rarely will the volume be substantially less or substantially more than 20 ounces. According to the empirical rule, for data having a normal or bell-shaped distribution, 68.26 or about 68% of the data values are within 1 standard deviation of the mean. 95.44% or about 95% of the data values are within 2 standard deviations of the mean. 99.74% or nearly all of the data values are within 3 standard deviations of the mean. An outlier is an unusually small or unusually large value in the data set. Z-scores are used to determine if observations are outliers. A data value with a z-score less than -3 or greater than 3 might be considered an outlier. However, such a value could have been incorrectly recorded. For example, a person conducted a survey might have heard a respondent say 17 when she meant to say 70. Or the person conducting the survey could have recorded a response equal to 23 as 32 by mistake. A data value with a large or very small z-value could be the result of incorrectly including an observation in the data. For example, if you are studying female heights and weights and a person you survey says they are male, but you think they said female, this could potentially contaminate your analyses because men tend to be taller and tend to weigh more. The large z-value or the unusually small z-value could be a result of an observation that was correctly recorded. In totem, z-scores reveal how data is distributed, while each individual z-value suggests whether an observation is an outlier or not. In the table below, for each of the 50 observations, we want to answer the question, is the observation within 2 standard deviations? If the absolute value of the z-score is less than 2, the answer to this question is yes. But the answer is no if the z-score is larger than 2. The first observation is within 2 standard deviations from the mean because the absolute value of its z-score is 1.93, which is less than 2. The second observation is within 2 standard deviations from the mean because the absolute value of its z-score is 1.57, which is less than 2. The third, fourth, fifth, and sixth observations are within 2 standard deviations from the mean because the absolute value of their z-scores is 1.21, which is less than 2. The seventh observation is within 2 standard deviations from the mean because the absolute value of its z-score is 1, which is less than 2. In fact, this observation is within 1 standard deviation of the mean. The 49th observation is within 2 standard deviations from the mean because its z-score is 1.86, which is less than 2. Everything between it and the 7th is within 2 standard deviations as well because the data are in ascending order. The 50th observation is not within 2 standard deviations of the mean because its z-score is 2.15, which is greater than 2. Because the observations were in ascending order, all but the final observations, whose z-score is 2.15, are within 2 standard deviations of the mean. Hence, 49 of the 50 observations are within 2 standard deviations of the mean, which is 98%. The empirical rule says about 95% of the observations are within 2 standard deviations from the mean, while Ch3's theorem says 75% of observations are within 2 standard deviations of the mean. Since the most extreme value is the maximum of 109, and it has a z-score of 2.15, all, or 100% of the observations, are within 3 standard deviations of the mean. The empirical rule says nearly all of the observations are within 3, while Ch3's theorem says 89% of the observations are within 3. None of the observations in the Hudson Auto Repair sample data are outliers because the largest z-score in absolute value is 2.15, which is less than 3. Covariance and correlation are measures of how close the relationship is between 2 variables. Winning percentage of the football team and attendance at home football games are going to be positively related. Hence, their covariance would be positive, while their correlation would be close to 1. If these measures are computed using sample data, they are called sample statistics. If these measures are computed using data from the population, they are called population parameters. The procedure used to compute a sample statistic is referred to as the point estimator of the corresponding population parameter. When numbers are substituted into the procedure, the resulting number is a point estimate of the population parameter. The covariance equations are similar to the variance equations. Each deviation from x's mean is multiplied by the corresponding deviation from y's mean, which are then summed up. After summing the products of deviations from population means, the population covariance is divided by the size of the population, capital N. The result is the population covariance. If the sum of products of deviations from the sample means is divided by the sample size, the resulting statistic is a biased estimator of the population covariance. Dividing instead by degrees of freedom yields unbiased estimator of the population covariance. Reed Auto Sales has figured out that the more they advertise, the more cars they generally sell. According to the sample of data they have collected, the company sold 14 out of 17 cars when it ran 1 TV ad. Sold 18 cars when it ran 2 TV ads, and sold 24 and 27 cars when it ran 3 TV ads. Summing up variable X's observation yields 10 TV ads. Dividing this by 5, the number of observations yields variable X's sample mean, which equals 2 TV ads. Summing up variable Y's observations yields 100 cars sold. Dividing this by 5, the number of observations yields variable Y's sample mean, which equals 20 cars sold. The 5 deviations from the sample mean of X are found by subtracting all 5 observations of X by X bar, which equals 2 ads. The square deviations from the sample mean of X are equal to 1, 1, 0, 1, and 1 squared ads. Summing up X's square deviations yields 4. Dividing this by the degrees of freedom, 5 minus 1, yields a sample variance of X, which equals 1 ads squared. The square root of this is the sample standard deviation of X, which equals 1 ad. The 5 deviations from the sample mean of Y are found by subtracting all 5 observations of Y by Y bar, which equals 20 cars. The square deviations from the sample mean of Y are equal to 36, 16, 4, 9, and 49 squared cars. Sum of Y square deviations yields 114. Divide this by the degrees of freedom, 5 minus 1, yields a sample variance of Y, which equals 28.5 squared cars. The square root of this is the sample standard deviation of Y, which is equal to 5.34 cars. The products of deviations from the sample means are computed by multiplying the values of x minus x bar column by the corresponding values in the y minus y bar column. The product of x's first deviation from the sample mean minus 1 adds, and y's first deviation from the mean minus 6 cars equals 6 add cars. The negative times a negative is positive, which is why this is 6. The product of x's second deviation from the mean, 1 add, and y's second deviation from the mean, 4 cars, equals 4 cars adds. The remaining products of deviation from the sample means are computed in similar manner, which are 0, 3, and 7 adds cars. Summing up this yields 20. Dividing this by the degrees of freedom, 5 minus 1, yields a sample covariance equal to 5 adds cars. The scatter plot of this data is graphed in the diagram below, which has the number of TV ads on the x-axis and the number of cars sold on the y-axis. In the first observation, the car lot ran 1 TV ad and sold 14 cars. Second observation, the car lot sold ran 3 TV ads and sold 24 cars. In the third observation, the car lot ran 2 TV ads and sold 18 cars. In the fourth observation, the car lot ran 1 TV ad and sold 17 cars. In the fifth observation, the car lot ran 3 TV ads and sold 30 cars. The scatter plot explicitly shows there seems to be a positive relationship between TV ads and cars sold. The relationship is not perfect. The plotted points do not lie on the trend line, but lie near it. The point corresponding to the means of the two variables, 2 TV ads and 20 cars sold, always lies on the trend line, which is also known as a regression line. Estimating the regression line is the focus of the final topic covered in advanced statistics. The covariance is difficult to interpret because its units are odd. Recall the units of the sample covariance in the Reed Auto Sales example. They were adds cars. What the heck is an add car? The correlation fixes this issue. The correlation is a measure of linear association, not necessarily causation. High correlation between two variables does not mean that one variable is the cause of the other. For example, hot dog sales at football games and the football team's winning percentage are highly correlated. This does not mean that the team will win more games if you sell more hot dogs at home games. A high winning percentage increases attendance, and high attendance increases hot dog sales. So winning percentage is the cause of attendance, and attendance is the cause of hot dog sales. The sample correlation coefficient is computed by dividing the sample covariance, S sub xy, by the product of sample standard deviations, S sub x and S sub y. The population correlation coefficient is computed by dividing the population covariance, sigma sub xy, by the product of population standard deviations, sigma sub x and sigma sub y. In the Reed Auto Sales example, the sample covariance, S sub xy, was equal to 5 adds cars. The sample standard deviation of x, S sub x, was equal to 1 add. The sample standard deviation of y, S sub y, was equal to 5.34 cars. The sample correlation is the ratio of the sample covariance, S sub xy, and the product of sample standard deviations, S sub x and S sub y. The sample covariance was 5 adds cars, the sample standard deviation of x was equal to 1 add, and the sample standard deviation of y was equal to 5.34 cars. The units of these statistics cancel out, hence the sample correlation coefficient is equal to 0.9363, In most cases, the closer the sample correlation coefficient is to positive 1, the closer the points lie near a positively sloped trend line of the scatter plot. In most cases, the closer the sample correlation coefficient is to negative 1, the closer the points lie near a negatively sloped trend line of a scatter plot.